Hi friends. Today we'll be starting our last chapter in second year physics. That is semiconducting devices, please. Okay. And from this chapter, we also will be getting around 2 marks in MSET. Okay. Around 1 to 2 marks from semiconducting devices. Semiconductors. We're getting around 2 marks from this chapter. Okay. This is the last chapter, around 13th chapter in our second year. 13th chapter. Now, first of all, to begin with, and according to our MSET syllabus, let us know about what are conductors, what are semiconductors, and what are insulators. Okay. For example, if you go briefly regarding conductors, see, we all know the lowest band level is called as valency band, and this one is called as conduction band. So here, if you observe carefully in conductors, both the bands will be overlapping. There is no energy gap. No energy gap. And if you observe carefully, it was found in conductors. That means any metals like iron, steel. Okay. The number of free electrons is found 27 per meter cube. And free electrons, any metal if you take, so many free electrons are there in any metal. Okay. 10 to the power of 27 electrons per meter cube. This is regarding conductors. In the same way, if you see insulators, in insulators it was found around only 10 power 7 electrons per meter cube. And in semiconductors, it was found around 10 power 17 electrons per meter cube. So, the free electrons, available electrons for conductors are very large. You can see, small potential is enough to conduct electricity. 10 power 27 electrons per meter cube. Insulators, little lesser, more lesser, 10 power 7. And semiconductors, 10 power 17. And if you observe carefully here, there is no energy gap between valency band and conduction band. If you observe carefully, valency band, what is valency band? See, generally in valency band, the free electrons are available. Okay? When sufficient heat or energy is given, when sufficient heat, E is equal to h nu or heat, radiation or heat is given, the electron will try to jump to the higher level, from lowest level to higher level. And we already known in the atoms chapter of the jumping action and energy levels also. For a hydrogen atom, you have seen from minus 13.6, 3.4. Okay, you have seen some values, minus 1.51, minus 0.85, minus, like that you have seen from ground state, first excited state, second, like that. You have seen the energy levels for hydrogen atom. That is from the formula minus 13.6, Z square by N square, electron volt. This is the energy, total energy level, from ground state to the higher level. You have seen the energy levels. So when sufficient heat energy or energy is given to the electrons, they will be jumping from valency band to conduction band. This is conductors. Now if you observe insulators, insulator you can take large energy gap, you can take for insulators. For insulator you can take between valency band and conduction band, energy gap will be more. Okay, this is energy gap for more for insulators, like plastic. Okay, best example for you can take as plastic as insulator. In some cases dry wood. Okay, pure water also is taken in insulator, some cases, but generally plastic. And then the last one, if you take semiconductor, between conduction band and valency band, this energy gap is little lesser than this one. This is having more energy gap. Okay, this is having more energy gap. So you can see here, it was found that for conductors, energy gap is around. Conductors energy gap anunda. So here energy gap is 0 electron volts. No energy gap because conduction band overlapping on valency band. So energy gap asal ledu. So that is why easily we can conduct electricity for conductors. Whereas you can see insulators and semiconductors, you can observe energy gap is there, that is more than around 3 electron volts. In this case, energy gap is more than 3 electron volts. In this case, the energy gap is more than 3 electron volts in insulators. Okay? And in the same way, if you see the last one for semiconductors, because the best examples are germanium and silicon. Germanium and silicon, that is fourth group elements in periodic table: carbon, silicon, germanium, tin, lead. So this is the best example for the semiconductors because it is acting in dual nature. In semiconductor, if you observe the energy gap, it is less than 3. So here it is less than 3 electron volts. These things are important for the examination. Energy gap in the semiconductor like germanium, silicon is less than 3 electron volts, and here it is more than 3 electron volts. Okay, and you can see it is less than, and the value also I am giving for you nearly 0.74 electron volts. So the value nearly around 0.74 electron volts, less than 3 electron volts it is. Okay, for germanium. Okay, for germanium, this one is germanium. For germanium the value is 0.74 electron volts it is for germanium. Okay, and he has given for silicon also, you can write down nearly 1.1 for silicon. For silicon it is 1.1 electron volts. Silicon ki 1.1 value, and for germanium 0.74 electron volts for germanium. Okay, and silicon it is around 1.1 electron volts. So here you can observe the energy gap is less than 3 electron volts. Here energy gap is more than 3 electron volts. Okay, diamond also you can take as example for insulator. Diamond. Okay, diamond also you can take as an insulator, please. Clear? Right. So more than 3 kabatti, it is around like I think 6 electron volts. Because already I told you in insulator, energy gap is more than 3 electron volts. So for diamond you can take around 6 eV electron volts, the energy gap. Okay, diamond you can take it as 6 electron volts nearly. So this is the basic structure of the conductors, insulators and semiconductors. Semi enduk cheppanante, it behaves as sometimes as a conductor depending on the temperature rising or falling, and sometimes it is an insulator. And here no energy gap, 0 electron volts. Energy gap is more than 3 electron volts. For diamond it is around 6 electron volts, and here for silicon it is 1.1 eV, and for germanium it is nearly 0.74 electron volts. Okay, now let us study about the conductivity and specific resistance of these three. Okay, now let us study about the, I am rubbing the figure. Let us study about the specific resistance or resistivity. Here material, here rho, and here is sigma. Sigma is equal to 1 by rho, and this is called as what? Conductivity. I'll write on the top, conductivity on the top. Specific resistance or resistivity, and this is inverse of rho, that is sigma, conductivity. So the basic things and the units tells ka the ohm meter, and this is Siemens per meter, because 1 by ohm meter unit, that is 1 by ohm into 1 by meter. 1 by ohm is mho, and mho is nothing but Siemens. So Siemens per meter is the unit. Clear? So the rho value for different, for example, conductors rho value is taken as conductors. For conductors the value is around 10 power minus 2 to 10 power minus 8 ohm meters. And this is reverse kabatti 10 square to 10 power 8 because 1 by rho kada sigma conductivity. So 10 square to 10 power 8 Siemens per meter. In the same way, conductors are the next one into manaki insulators. For insulators, we have the value around 10 power minus 5, 10 power minus 5 to 10 to the power of 6 ohm meters. And this is reciprocal kabatti, ee value enta vali 10 to the power 5 to 10 to the power of minus 6 Siemens per meter because reverse adi reciprocal. In the same way, last one, this value, sorry, it is for semiconductors. This one, this is for semiconductors, not insulators. This is for semiconductors, please. Sorry, this is for semiconductors. And last one is for insulators. This is for 10 power minus 5 to 10 power 6, and the conductivity is 10 power 5 to 10 power minus 6. And last one, insulators, 10 power 11 to 10 power 11 to 10 power around 19, 10 power 11 to around 10 power 19 ohm meter, and this is reverse, inverse, 10 power minus 11 to 10 to the power minus 19 Siemens per meter. Okay, please check the value because in the examination they may be asking 10 power 11 to 10 power 19. Okay, and reverse 1 by rho kabatti the sigma 10 power minus 11, 10 power minus 19 Siemens per meter. These are the values of specific resistance or resistivity, and inverse of that one is conductivity values for different materials. Please make a note of this one, write the values correctly. Okay, right. Now let us go to, after learning about these things, what is a semiconductor pure and how it is becoming impure, in what fashion. Let us study one by one clearly. Okay, right. Now see here, how can you tell the semiconductor is a very pure semiconductor and how it is becoming impure, please. Okay, for that I'll explain with a neat figure. Pure semiconductor, please. Okay, pure semiconductor. See, generally semiconductors can be two types. One is intrinsic and second one is extrinsic. So intrinsic is called as pure one, extrinsic is nothing but impure. That means doping is done. I will explain later on that one, impure one. Impure, and it is divided into P type and N type extrinsic semiconductors. So let us first learn about intrinsic, pure. So pure lo ఏమవుతుంది, ఆ covalent bonds ఎలా ఉంటాయో ఒకసారి చూద్దాం. For example, if I take silicon structure. If I take pure silicon structure, because just now I told you carbon, silicon, germanium, tin, lead. Carbon, silicon, fourth group elements in periodic table. Fourth group, carbon, silicon, germanium, tin and lead. Silicon, germanium are best semiconductors. So if I take silicon, because it is belonging to fourth group elements, it can have 4 covalent bonds successfully. 1, 2, 3, 1, 2, 3, 4. Again 1, 2, 3, 4. 4 covalent bonds it can make successfully, please. Because it is belonging to what? Fourth group element. Okay? So it can make 4 covalent bonds successfully. You can see the structure here. This is the basic structure. So in pure, what is happening? There will not be any unpaired, you can see. Chudandi okasari. This is one bond, covalent bond. One covalent bond. This is another one. This is one covalent bond. This is another covalent bond pairing, sharing a pair of electrons between the two atoms. This is another one. This is the outside, another one. This is another one. And you can see sharing a pair of electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in the outermost. Okay, this is again. So you can see there is no unpaired econ because it is a pure one. Unpaired ekkada ledhu meeku find cheyandi. You can see sharing a pair of electrons is outside. Again you can continue. See, this is how the structure will be. So if you take silicon or germanium, see, no unpaired. That means ఏది కూడా గ్యాప్ మిగిలిపోలేదు. Clearly you can see 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. So a covalent bonds are forming here, sharing a pair of electrons. Because it is belonging to fourth group, it can make 4 covalent bonds. 1, 2, 3, 4. 4 successful. 1, 2, 3, 4. One ido bond, ido covalent bond, ido covalent, ido. You can make 4 covalent bond. 1, 2, 3, 4 or 1, 2, 3, 4. Okay, na? 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. So it can make successfully in pure. Because pure there is no excess of electrons or holes. In this case, number of electrons will be equal to number of holes, please. And we already learned in current electricity what is Q. Q is equal to IT and that is equal to NE. Okay? Let IT is equal to NE or I is equal to NE by T. Strength of current is equal to number of electrons into electron charge by time taken. Strength of current. So in this case pure, number of electrons is equal to number of holes. And you all know in the band theory, in the valency band, electrons are there. When sufficient energy is given, E is equal to h nu or heat energy, electron will be jumping to the conduction band. So when these electrons are jumping, holes are formed here. And here electrons will be there. So if you observe carefully, number of holes, suppose 4 are there, 4 electrons, 5 are there, 5, 10 are there, 10. So Ne is equal to NH. In the case of pure semiconductor, because there is nothing effect, no extra electrons or no extra holes are there. Number of holes is equal to number of electrons. So for the correct conductivity, you can take the equation as I is equal to Ne by T. Number of electrons into charge by time taken. Clear? Any doubt? And I already have given the energy gap for silicon and germanium in the before case. For germanium it is 1.1. It is given by 1.1 for pure silicon. See, for pure silicon, the energy gap 1.1 electron volts pure, and for pure germanium it is 0.72. Energy gap for is 0.72 for pure germanium. Pure germanium value is 0.72, silicon is 1.1 electron volts. That is energy gap. Clear? And one point you have to observe. Have you drawn the figure? Clear? Very good. So here no excess of electrons are there or holes. Number of holes are equal to number of electrons. So this is a case of pure. Now let us see if any impurity is added, then what happens. Let us explain those also. Clear? Right. Now pure case lo baane undandi, pure semiconductor, pure germanium, pure silicon. Energy gaps also you have seen. Energy gap values you have seen. For energy gap for pure silicon is 1.1 eV and 0.72 eV is for pure germanium. Now for example, doping is there. For example, before going to doping, I want to tell you one point regarding semiconductors. Regarding semiconductor, at 0 degrees Kelvin, at 0 degrees Kelvin anta minus 273 degrees centigrade. Ante kada 0 degrees ante, what is 0 degrees Kelvin? At absolute temperature. At absolute temperature 0 degrees Kelvin అంటే చూడండి, Normally for centigrade scale, how Kelvin is added? For example, 0 degree centigrade only. To convert into Kelvin, what you will do? Plus 273. When you add 273, you will get how much? 273 is Kelvin. And the conversion of centigrade to Kelvin, if 0 degree centigrade is there, you add 273, you will get 273. In the same, if Kelvin is there, minus 270, you will get 0 degree. So at 0 degrees Kelvin and absolute 0. Absolute 0. And in centigrade length అవుతుంది 0 minus 273. That is minus 273 degrees centigrade ఇది. At minus 270 degrees centigrade, or if you add 273 for this one, you will get 0 degrees. So at 0 degrees Kelvin అంటే టెంపరేచర్ బాగా తగ్గించేస్తే semiconductor, what happens? The energy gap decreases and it becomes insulator. Very, very important point. The energy gap completely decreases. Overlapping of valency band and conduction band. Not decreases. Energy gap ఏమవుతుందంటే పెరుగుతుంది ప్లీజ్. It becomes insulator. Okay. So energy gap అంటే between valency band and conduction band, energy gap is increased. ఎందువల్ల? Because of the decrease in temperature. At 0 degrees Kelvin, when the temperature decrease, it is an insulator. Insulator అంటే ఏంటి? Energy gap పెరిగిపోతుంది. But again, when you raise the temperature, what happens? జాగ్రత్త అర్థం చేయండి. ఇన్సులేటర్లో ఏమవుతుంది? You can see here. Gap is there, energy gap is there. Already I have given the value for you. Okay? So what happens at 0 degrees Kelvin? It is an insulator. But when you increase the temperature, again it becomes a conductor. When temperature is raised, ఏమవుతుంది? Valency band, conduction band overlaps on each other. No energy gap, it becomes conductor. It is a conductor. So this question is very, very important regarding semiconductor. At 0 degrees Kelvin, a semiconductor is an insulator. Energy gap is coming. But when temperature is raised, at 0 degrees Kelvin అంటే minus 270 degrees centigrade. When temperature is raised, energy gap decreases. It becomes a conductor. This point is very, very, very important. Clear? Right. Now let us study about doping. ఈ పాయింట్ చాలా ఇంపార్టెంట్ ఎగ్జామినేషన్ అడుగుతున్నానండి. At what temperature a semiconductor is an insulator? At absolute temperature, that is at absolute 0 degrees Kelvin. An insulator is a semiconductor is an insulator, and when temperature raise, again it becomes a conductor. Energy gap decreases. Energy gap increases, energy gap decreases. Clear? Now let us go to the next thing, that is doping. What is doping? See, we all know regarding doping, and this doping is also done in Olympic Games when athletics are making some 100-meter sprint or anything, because what happens is doping means an impurity is added. Okay? Impurity and enti? That means, for example, for a pure semiconductor, I told you just now with the diagram, no extra electrons or no extra holes are there. For like pure semiconductor, like pure germanium or pure silicon, if selected impurities like 3A group elements or trivalent elements, like 3A group elements and enti? Boron, aluminum, gallium, indium, thallium, like 3A group elements or trivalent elements are taken as a selection, boron, aluminum, gallium, indium, thallium, and added into the pure semiconductor, then it becomes a contaminated. That means it becomes extrinsic. So this type is called as P type. When 3A group is added, it is called as P type. If suppose 5A group element is added, 5A, pentavalent or 5A group elements, fifth group element and fifth group elements. If fifth group is there like nitrogen, phosphorus, arsenic, antimony, bismuth, like these elements are taken and added into pure semiconductor like germanium, silicon, then it is called as N type. That means while doing this doping, what happens is some unpaired will be there. అంటే ఈ కోవలెంట్ బాండ్ బ్రేకేజ్ వస్తుంది. ఐదర్ హోల్స్ విల్ బి మెజారిటీ ఆర్ ఎలక్ట్రాన్స్ విల్ బి మెజారిటీ. హోల్స్ అయినా మేజర్ అవుతాయి లేదా ఎలక్ట్రాన్స్ అయినా మేజర్ అయిపోతాయి. సో లైక్ దిస్ ద కండక్టివిటీ కెన్ బి ఇంక్రీజ్డ్. కండక్టివిటీ కెన్ బి ఇంక్రీజ్. క్లియర్ హియర్? సో ప్యూర్ సెమీకండక్టర్ డోపింగ్ చేసి సెలెక్టెడ్ ఇంపీడ్ బొరాన్, అల్యూమినియం, గ్యాలియం, ట్రైవాలెంట్ ఎలిమెంట్స్, 3A group elements లేదా pentavalent elements, nitrogen, phosphorus is added into the germanium silicon of pure, it becomes N type. Okay, now let us study about the structure of P type and N type. Structure of P type and N type extrinsic semiconductor. Okay na? So for example, if you take P type extrinsic semiconductor. So P type లో ఏం చెప్పాను మీకు? Take the elements of 3A group elements like boron, aluminum, gallium, indium, thallium. Now we already know pure germanium or pure silicon. You can take the germanium and silicon. Pure germanium or silicon, you can take the semiconductor example. Okay. Now what I will do, instead of boron I will take aluminum. Okay, I will take aluminum. Now again I will form the structure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I have taken silicon. Silicon belongs to what? Fourth group element. Silicon belongs to fourth group element. Carbon, silicon, germanium, tin, lead. So it can make 4 covalent bonds successfully. 4 covalent sharing a pair of electrons between the atoms. So ఒకసారి జాగ్రత్తగా అది గీద్దాం. సిలికాన్, 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 సిలికాన్. So let us see, it is making 4 successful, you can see. It is making 4 successful covalent bonds because it belongs to fourth group element. So 4 covalent bonds successful ga cheyagalaru. You can see the structure here. 1, 2, 3, 4, 1, 2, 3, 4 and 1, 2, 3, 4, 1, 2, 3, 4. So observe carefully, and middle what we'll do is we'll take away one silicon and put aluminum as doped atom. I'll take aluminum as the doped atom, please. Are you following? I'll take aluminum as the doped atom. తీసుకున్నట్టుగైతే అల్యూమినియం ఏంటి? బిలాంగ్స్ టు 3A group element. Boron, aluminum, gallium and thallium. So this can make only 3 successful covalent bonds. 4 చేయలేదు because it belongs to 3 electrons are the free electrons are there. So జాగ్రత్త చూడండి ఏమవుతుంది ఇక్కడ? Successful bond, successful bond. Okay, successful bond here, successful bond here, successful bond 1, 2, 3 and this becomes unpaired. Adavadna? See, it makes 1 successful aluminum, another successful, another 3 successful bonds avutundi. 4th bond becomes unpaired and this becomes as a whole. 4th is unpaired, this becomes whole. Ikkada bond form avadu. You can see here bond formation is there, empty, unpaired it is, unpaired because of no electron. Electron ఖాళీ అయిపోయింది, లేదు ఇక్కడ ఎలక్ట్రాన్ 3 ఉన్నాయి, 3 electrons outermost. So it can make 3 covalent bonds successful. Remaining all are okay. Remaining all are okay, you can see. Remaining all it is successful. See? Remaining all are successful. So this is unpaired here. So like that what happened, not one hole, లక్షల్లో ఉంటాయి, millions holes are there like this in this P type of extrinsic. So అందువల్లే in P type the majority charge carriers are holes. The majority charge carriers are number of holes are greater than number of electrons. ఇలాంటివి ఎన్ని ఉంటాయి, ఒకటి కాదు, lakhs will be there, holes, millions. So number of holes are greater than number of holes in p type. Are you following now from the basic structure? Here it is unpaired. It is making only 3 covalent bonds successfully. 1, 2, 3. Fourth one is unpaired. So therefore, number of electrons in this one will be, number of holes will be more. Holes make hole current. Tells kada? Hole is taken as positive charge, positive current. And electron is taken as negative current. Negative current. Holes make positive current. So here majority will be holes. Majority charge carriers, holes. And minority are electrons. Clear? Right. Now let us go to the same thing, next item. Next item I'll take. Same thing. That is n-type. So in n-type extrinsic what happens we'll see. n-type. ఇప్పుడే చెప్పాను కదా n-type ఎలా ఏర్పడుతుంది. Here n-type what did I tell you? Fifth group element or pentavalent. To formation, in the formation of n-type, fifth group, pentavalent, like nitrogen, phosphorus, arsenic, antimony, and bismuth is taken. In this case, what I'll take? Phosphorus I'll take better as the impurity. In this case, I'll take phosphorus as the impurity. And as you know, again silicon germanium belongs to fourth group. They can make 4 successful bonds, silicon, 4 covalent successfully. And you have taken fifth group element 5, and it can make 5 covalent bonds. Phosphorus belongs to fifth group, pentavalent, so it can make 5 covalent bonds successfully. And అర్థం ఏంటి చూడండి, ఇక్కడ చూడండి, 1 bond successful, second bond successful covalent, third successful, fourth one is also formed here, you can see fourth one. And excess of electrons are there, excess of electron. So here you can see it is making very clear, first bond, second, third, fourth, fifth is ready, excess is there. Like this again in millions and lakhs will be there, lakhs or in millions electrons. So therefore in n-type the majority charge carriers are electrons than holes. ఇలాంటి electrons bold ఉంటాయి in millions and lakhs. Okay, so here excess of electron, because the covalent bonds are exceeding, it can make 5, 4 already successful made, fifth one extra is there. So it is also called the electron donor. And p-type electron acceptor. This is electron donor, and in p-type it is acceptor because vacancy is there, it cannot give, it can accept, and it is electron donor or electron acceptor. Clear? So this is how the concept is explained regarding p-type, n-type, and also the basic structure of the covalent bonds regarding p-type extrinsic and n-type extrinsic semiconductor. Clear? Any doubt? See, these are very, very important in the examination regarding NEET and MSET. Regularly they are asking in the examination. Clear? So in p-type, number of holes are greater than number of holes, p-type. Majority are charge carriers, holes. In n-type, number of electrons are greater than number of holes in n-type. Please make a note. Here majority charge carriers are electrons. So electron acceptor, electron donor. It can give this is electron acceptor. P-type. Because vacancy is there. Voids are formed. Holes are majority. Here more electrons are there, we can give electron donor. It is acceptor. Clear? And we have one formula also, Ne into NH is equal to Ni square for numerical problems in MSET. Sometimes you can take Ne into NH is equal to Na whole square, which is used for numericals, please. Okay. In the numerical problems, you can use this formula. Ne, number of electrons and number of holes. Number of electrons into number of holes is equal to Ni whole square. Okay. The current whole square. This is a formula you can utilize for the numericals. Any doubt? So are you following the concept here? The formulas and other things. See, these formulas are very, very, very important while solving numericals, please. So you can use this formula. Ne into Nh is equal to Ni square. Number of electrons into number of holes. Okay, ఇది కొంచెం suffix రాద్దాం. NH ఇది suffix. Ni. NH. Ni. Number of the current square. Current మీకు already చెప్పాను కదా, what is Q? Q is equal to IT, that is equal to Ne, or I is equal to Ne by T. So like this you can calculate the current by using current electricity concept. Okay. Now let us go to the next one. Let us go to the next one, please. That is PN junction diode, depletion layer, okay, and potential barrier. Let us study next one. PN junction diode. PN junction diode, depletion layer, and potential barrier. One by one. Now what is PN junction diode? For example, see here, when P type and N type both are brought together and joined, a junction is formed. A junction is formed. Okay? These two acts as two terminals, positive terminal, negative terminal. And this is the symbol for PN junction diode. Okay? This is what? Symbol for PN junction diode. PN junction diode. Diode means two terminals only. One positive, P type, and this is N type, negative. So when P type and N type both are coming and joined, single junction, one junction is formed. That is called as PN junction diode. Clear? Now in this case, what happens we'll see. Please draw this figure. In this case, what happens we'll try to study. See, as I told you, in P type, what are the majority? Holes. What are the majority charge carrier? Holes. Positive charge. Okay, na? So positive charge. Positive charge. So here N type, what are the majority in N type? Electrons, negative charge. Okay, electrons, negative charge. So when both are joined, what happens? When both are joined together, please make a note here. One junction is formed, and what is happening here we'll try to explain. So of course this is positive charge, P type, and this is N type, electrons, negative charge. So when both are joined, what happens? Some electrons will be jumping in here, in P type, and P type holes will be jumping in N type. They will get neutralized. P loంచి కొన్ని holes N లోకి, N లోంచి electrons P లోకి వెళ్ళి, they will get neutral and exchange the charges. And what happens after some time? Here, these electrons will enter into here. I'll put it here best. Here, these electrons will enter here, and P type holes నుంచి కొన్ని N type లోకి enter అయిపోతాయి. They will exchange the charge. And ఇక్కడ ఏంటంటే పాజిటివ్ వచ్చేస్తాయి. ఇది పాజిటివ్, ఇది నెగిటివ్, and they become immobile. అంటే ఇంకా they will stop coming. No more exchange. That means no more electrons will come into P type and no more holes will come into N type. They will behave like a security guard there. So here immobile charge carriers exist. అంటే ఇందులో కొన్ని ఎలక్ట్రాన్స్ ఇక్కడికి వస్తే పీలో హోల్స్ అందులో వెళ్ళిపోయి దే విల్ ఎక్స్చేంజ్ ద చార్జ్. సో హియర్ వాట్ హ్యాపెన్స్, హియర్ దిస్ బికమ్స్ పాజిటివ్ అండ్ దిస్ బికమ్స్ నెగిటివ్ అండ్ the potential will be in this direction now, field direction, and of course it is imaginary and it is not really imaginary. This barrier is called as potential barrier. Okay, a potential which exists at the junction of pn junction lo edaithe potential raise avutundo that is called as potential barrier. A potential which is existing at the PN junction diode is called as potential barrier. Of course it is imaginary. Of course it is imaginary. So you can see here potential positive becomes here negative. So field ఎటువైపు ఉంటుంది, పాజిటివ్ నుంచి నెగిటివ్ ఇన్ దిస్ డైరెక్షన్. ఫీల్డ్ ఎటువైపు ఉంటుంది, పాజిటివ్ నుంచి నెగిటివ్ వెళ్తుంది కదా ఎప్పుడు కూడా. వాట్ ఇస్ ద బ్యాటరీ కనెక్షన్? Suppose like this you have given. So current will be in this direction. This is the direction of electrons. So in this direction, from positive to negative. This is positive and this is negative. So from positive to negative the direction will be there. And that barrier is called as potential barrier. And here a small layer is formed. Here a small layer. This layer is called as depletion layer. Small layer exists. That layer is called as depletion layer. Now you may ask some questions. Sir, how to remove this layer? How to reduce the thickness of the layer, the depletion layer? And this is reduced by biasing. That is our next process called as forward bias and reverse bias condition. Clear? Right. So this is about PN junction diode, depletion layer, potential barrier. So whatever barrier potential is, this is an imaginary one, not real one. Okay. So ఈ పొటెన్షియల్ ఏమవుతుందంటే పాజిటివ్ నుంచి నెగిటివ్, నెగిటివ్ దే విల్ ఎక్స్చేంజ్ ద చార్జెస్ అండ్ వన్ లేయర్ ఇస్ ఫార్మ్డ్. ఓకే, నౌ వాట్ హ్యాపెన్, దే విల్ ఎక్స్చేంజ్ అంటే ఇక్కడ నెగిటివ్ దగ్గర పాజిటివ్ అయిపోతుంది. ఇన్ ద పాజిటివ్ నెగిటివ్ ఇట్ ఈస్ బికమింగ్. సో పొటెన్షియల్ విల్ బి ఎగ్జిస్టింగ్ ఫ్రమ్ దిస్ సైడ్ నౌ, దిస్ సైడ్. ఓకే, సో ఇక్కడ పాజిటివ్ ఇక్కడ నెగిటివ్ ఫార్మ్ అయిందండి. ఇక్కడ పాజిటివ్ నెగిటివ్, యూ కెన్ అబ్జర్వ్ కేర్ఫుల్లీ, పాజిటివ్ అండ్ నెగిటివ్, and that is potential barrier. Clear? Now we will explain how to remove the thickness of the layer, and that is nothing but forward and reverse bias condition. How to remove that layer? Now we will explain next one, that is called as forward bias and reversed bias. Now what is forward bias? Suppose if P type is connected to positive terminal of the battery and N type is connected to the negative terminal of the battery, and suppose if an ammeter is connected to find out the current. Now here you can see this is P type, current direction is going this direction, electron will be in this direction, opposite. This electron direction, ఇప్పుడు కూడా తెలుసు కదా, current ki opposite electron direction. Okay, it goes like this, again comes like this. This is electron direction, this is current direction, going and coming. You observe carefully here in forward bias condition, layer ఏమవుతుందో observe చేయండి. What happens to the layer, depletion layer? Is it decreasing or increasing? Let us study here. So when the current is going, this is positive charge. Positive, positive, what happens? Ripple. Positive coming towards the positive, what happens? Ripple. And again come here, negative charge, negative, negative, ripple. So when the ripple each other, what happened to the layer? Layer will be decreasing. Okay, when layer is decreasing, what happens? There is a conduction, ammeter will be showing reading, current will be passing. Current will be passing. So అందుకే in forward bias condition current will be flowing in the circuit in forward. In the same thing if you apply for reversed, the same thing if you apply for reverse bias condition. Okay, P type and N type. Reverse bias and P-type is connected to the negative, N-type is connected to the positive terminal. Okay na? P-type is connected to forward lo P is positive. Now P is connected to negative. And if suppose if a microammeter, here milliammeter, here microammeter and a 10 power minus 6 plus minus. P-type is connected to negative terminal. P-type is connected to negative terminal. N-type to positive. This is called as a reversed bias condition. In this case, if you observe what happens, you observe here negative terminal, positive terminal, the attraction. Negative, positive. ఇందాక రిపల్ అయింది, రిపల్ అయ్యి వేరు తగ్గింది. ఇప్పుడు ఏమవుతుంది? పాజిటివ్ ఇస్ కమింగ్ టువర్డ్స్ నెగిటివ్, అట్రాక్షన్. సో దిస్ నెగిటివ్ ఇస్ అట్రాక్టెడ్, నెగిటివ్ ఇస్ అట్రాక్టెడ్. ఇన్ ది సేమ్ వే పాజిటివ్ నెగిటివ్ అట్రాక్టెడ్ అగైన్. సో వాట్ హ్యాపెన్ దేర్ బై ద గ్యాప్ ఇంక్రీజెస్. గ్యాప్ ఇంక్రీజ్ అవుతుంది చూడండి, ఇంక్రీజ్ అలా. ఇది డిక్రీజ్, ఇంక్రీజ్. ఇంక్రీజ్ అయినప్పుడు ఏమవుతుంది? మళ్ళీ లేయర్ తయారైపోతుంది మీకు. సో ఆల్మోస్ట్ దేర్ విల్ బి నో కరెంట్ ఫ్లో ఇన్ ద reverse bias. But when you put a micro emitter, small amount of current is observed. Not completely zero, small amount of current, small amount of current is observed. In general, we say there will be no current flow in reverse bias, but if you put a micro emitter in reverse bias also, small amount. ఇక్కడ ఏం జరిగింది? రిపల్స్ అయింది, repulsive force. So layer is increasing, their attractive force, layer is decreasing. You can see layer is decreasing gradually. Here layer is increasing. You can see positive charge, negative charge, positive, negative, positive, they attract అవుతుంది. Positive charge comes, positive నుంచి నెగిటివ్ వెళ్తుంది. అలాగే ఇక్కడ చూడండి, నెగిటివ్ ఛార్జ్, ఇది నెగిటివ్, ఇది పాజిటివ్ ఛార్జ్, ఇది నెగిటివ్. సో ఏమవుతుంది? పాజిటివ్ నుంచి అగైన్ ది బోత్ అట్రాక్ట్స్. ఇది నెగిటివ్ ఛార్జ్, ఇది పాజిటివ్, both will attract, positive and negative, and it will be repulsive. So layer will be increasing. So like this, in forward bias and reverse bias condition, current will be flowing and not flowing in reverse, but small amount, very small. If you put microammeter, then you can find very small amount. Okay? And if you draw a graph also for this one, you will have like this. If you draw a graph for voltage versus current, voltage on x-axis and current and y-axis, see, it will be like this. Okay, this is the graph. This is forward bias condition and this is reverse bias. This is the graph for voltage versus current. Voltage on x-axis, voltage values, if you take on x-axis, and all current values. Okay, this is forward bias. You can see gradually yes, sorry for the interruption, small power cut is there. Now let us continue the chapter. See, we have drawn a graph for forward bias and reverse bias. You can see the graph slightly, slowly it is increasing, and exponentially it is increasing the value. In the same way here you can see in negative side also reverse bias. As I told you, reverse bias they will be completely cut off, but when you put a microammeter only small amount of current is observed. So these are the potential versus current graph in forward bias and reverse. Now let us go to the next one. Let us go to the next one after the graph, that is PN junction diodes are used as rectifiers. Okay, that is our next one subject. PN junction diode li rectifier laga ela use cheyachu. What is rectifier or what is rectification? What is rectifier or what is rectification? Rectification. See, rectification means converting AC to DC current, converting alternating current into direct current. That process is called as rectification, and which is making that process called as rectifier. So this PN junction diodes are used as the rectifiers. So in the examination syllabus you are having half wave and full wave. rectifiers. So parallelly I will explain each and everything. Half wave ante enti, full wave ante enti, parallelly. Okay. So how the AC to DC is converted output, we'll see. So half wave and full wave, I will draw a middle line, and this is half wave rectifier, and this is full wave rectifier. So we'll see the difference. See, in half wave, see, we'll give the circuit diagram first of all. Circuit diagram around it will be in this fashion. See, so you are giving AC input, okay, just it is like a primary coil, and you can see secondary, and here only one diode is used, only one diode, okay, and here one external load resistance will be there, RL, and this is output connection, this is output, this is input, okay, primary circuit, secondary circuit, this is secondary circuit. AC voltage is given here. I told you conversion of AC to DC, alternating current, direct current, is called as rectification. This is circuit diagram. In the same way, if you see full wave circuit, same AC voltage, AC input, okay, and if you here observe here two diodes are taken, D1 and D2, two diodes, and same fashion here one external load resistance output, and here one wire is conducted to earthing at point somewhere over here, some C, okay, earthing is there. This is the circuit diagram, primary circuit, secondary, input, output. Here two diodes are used, okay, here you can see only one diode, load resistance is there, primary and secondary. This is half wave and full wave circuit diagram. Now coming to the cycle diagram, that is input cycle. See here, so as you know, this is the full cycle for time t. This is full cycle, one cycle, and this is half cycle, t by 2. Input this one, and here output, same way for this one, input for full wave, and output for full wave. If you observe carefully here, you can see here how the function will be in this case. How the function in half wave, what happens is, when input is given in the first half cycle, it behaves as a forward bias, current flows. First half, it behaves as a forward bias, current flows. Second half cycle, reverse bias, current does not flow. This is plus minus, plus minus, plus minus, plus minus, so on. So here you can see current flows, current does not flow. Again next half cycle, current flows. So this is the output in the case of half cycle. So much of a gap is negative, no current. So first half cycle low, it will be in forward bias, current flows. Next half cycle, current does not flow, no current. Next it continue again, forward, again reversed. This is the output for half wave rectification. Coming to full wave low, children, rendu diodes unnai. So if suppose D1 is in forward bias, current flows, this is in reverse bias, first half cycle. First half cycle, T by 2, T. First half cycle, what happens? You can see. In first half cycle, This diode is in forward bias. This is in reversed. No current. Forward bias. So this will be in reversed. First half cycle, no current. Second half lo again this one forward. Second half and ikkadi. So that is why in this the current output is more. You can see more output is coming. Here output is less. The point because two diodes are connected here. First half cycle lo ఇది forward lo untadi, forward bias. This will be in reversed. So no current. Forward lo current undi. Second half cycle lo again this becomes in forward. So again positive current. So like that it will be making the full wave rectification. So more output is coming here. Clear? So that is why in this case output I will give an equation. See, I will rub this equal. Clear? I will rub this one because I have to give one formula for you. Efficiency. See, in the case of half wave, see, efficiency in half wave is generally given 0.406 into RL by RF plus RL. This RL is called external load resistance. External load resistance. RF, forward bias resistance. RF, forward bias resistance. 0.406 or 40.6% is the efficiency in this case. Half wave kabatti. But full wave lo full rectification is done. So then double 2 times. So in full wave, this is half wave. This is half wave efficiency, please. Efficiency 0.406 into RL, external load resistance value by forward bias resistance plus external load. Full wave efficiency 2 times avutundi. Dini 2 times in enta 0.812 because 2 6 are 12, 2 4 is 8. 0.812 into again external load resistance by forward bias resistance plus external load resistance. So in full wave, full value, that means 2 times the value of half wave. So in this fashion, the half wave rectification is done in 2 ways, in a half wave and full wave by using PN junction diode and diodes. Single diode, half wave. 2 diodes, full wave. And this formula is very, very important, please. Okay, 0.406 into RL by RF plus RL or 0.812 into RL by RF plus RL. RL is external load resistance. Clear? Any doubt? Right. Please note on this formula, these values are given, then you can apply in that one and you can calculate the efficiency of half wave rectifier. So finally, rectification means what? Converting AC current into DC current, alternating current into direct current by using PN junction diodes. Okay? So PN junction diodes are used as a rectifiers. Now let us go to the next one after rectification. What is a Zener diode? What is a Zener diode? Very, very important. ఈ Zener diode అంటే ఏంటి and what is the symbol? Okay, generally the symbol is taken in this fashion. And it is also called as voltage regulators. See, generally in our household purposes, we will be using Android TVs and big refrigerators. So to avoid heavy currents, to protect heavy currents like 440, 450 like that, this Zener diode will be acting as a voltage regulator. It will be acting as a voltage regulator. So Zener diode is, this is the main symbol of Zener diode. These are used as a voltage regulators. Like nowadays we are having so many in our market like V-Guard, Unistep. So all these will be having Zener diode. This is the structure of Zener diode. This is the structure of the Zener diode. So this will be acting as a voltage regulators. So let us see what is the function in the circuit. How it acts. Zener diode. For example, I will give a small diagram, circuit diagram, and make a note. Zener diode will always be in reversed bias condition. Reverse bias ante telusu kada? What is reverse bias? P type to the negative terminal and N type to the positive terminal. This is called as reverse bias, and it is heavily doped. It is heavily doped, please. Impurity will be heavily doped. Germanium or silicon. Heavily doped, reverse bias condition, please. In reverse bias condition, P type is negative and N type to positive. Clear? Now I am showing the diagram for this one, how it functions fastly. So in a Zener diode, what happens is, here, this is positive potential, this is negative, this is the resistance drop. I will explain why it is I am telling drop. And with this, as I said just now, P type connected to negative terminal, this is Zener diode kada, Zener diode. You can see N type is connected to positive terminal. Reverse bias, P type to negative, this thing. And for this one, we are also adding one external load resistance, please. This is earthing, and for this, an external load resistance we will be adding for this one, RL. And this external load resistance enti kadandi, this is nothing but the items, electrical appliances, whatever you are using. Electrical appliances you are using, like television, Android TV, refrigerator, washing machine, etc. Or washing machine you won't use, of course, you can't take washing machine. Like televisions and refrigerators, big electrical appliances, to avoid heavy currents. So this external load resistance, whatever, is nothing but the electrical appliances like TV and refrigerator. So what happens, how the function will go? So this is the circuit diagram. This is R drop resistance. Suppose normal current comes, for example 220, 230. So current will flow in this one. Current will flow and it will be at rest. Zener diode won't function now. Current will take, the TV will be on. Refrigerator, nothing problem. Suddenly, due to some problem in the transformer, for example 450 volt is coming, then the main function of Zener diode is the current will take this one. Zener diode will take more current. That is the main function. Zener diode will take more current. At the same time, what happens? There will be drop from your Kirchhoff's laws. Current direction, path, same direction. So what is the current here? V is equal to I into R. Suppose 440 is coming. 440 voltage here. Suppose the current is coming this direction. So what is the drop here? Resistance, suppose 100 ohms. Current of, for example, 2 amperes అనుకోండి. That is 4 amperes. 4 into 100 ohms. How much? 400 volts. That much voltage is dropped. Suddenly heavy voltage వచ్చిందండి, heavy voltage. So what happens? Suppose if that current goes into the TV will be gone within no time. So to avoid that function, to avoid the damage, a Zener diode is connected in the circuit, and this entire thing will act as a voltage regulator, like a V-guard or unistep. When heavy currents comes, the current will be taken by the Zener diode. Current will be taken by the Zener diode. It acts as a regulator. And the same way, the path and current in same direction kabatti, here there will be potential drop. So కొంత డ్రాపేజ్ వచ్చేస్తుంది. డ్రాప్ ఫర్ ఎగ్జాంపుల్ ఎంత ఇక్కడ చూడండి 400. సో ఓన్లీ 50 వోల్ట్ విల్ బి, ఫర్ ఎగ్జాంపుల్ ఐమ్ టెల్లింగ్ యూ, అంత డ్రాపేజ్ ఉంది. 4 amperes అనుకోండి, 4 into 100, 400 volts. So 440 minus 400, 50 volts will be go to the TV. Generally చెప్తాను. Like that it will be balancing. More voltage coming, it will be taking that Zener diode, and at the same time there will be potential drop. V is equal to IR. So heavy voltage is subtracted from this one, and only a few voltage is gone to the electrical appliances. So like this, the voltage stabilizer will be acting as a voltage regulator, the Zener diode. Clear? So this is the main function of the Zener diode as a voltage regulator, and it is operating in the reverse bias condition, okay, and it is heavily doped, please. Now let us go to the next one after Zener diode, that is junction transistors. Junction transistors. So generally already I told you we have PN junction, P type, N type. For example, one more P type is brought near right side, then it becomes PNP. Okay, you can say this is emitter, collector, base, and if you draw the circuit for this one, it will be in this fashion. This is circuit diagram, base, emitter, collector, and current will be in this direction, emitter to base, and this is called as PNP junction transistor. Now what is the use of this PNP and NPN? Junction transistors are mainly used as amplifiers. That means to increase more the sound to 100 times or 1000 times. That is called amplification. Whereas in PN junction diode, they are used as rectifiers. AC is converted into DC, direct current. Here what happened? These PNP or NPN junction transistors are used as amplifiers to increase more sound 100 times. So this is the circuit diagram. In the same way, if you go for NPN, this is PN. If left side one more N is taken, then you can see emitter, collector, base, and the circuit diagram. You can see here emitter, collector, base, and the NPN current goes from base to emitter. In NPN junction transistor, current will be going from base to emitter. So this is basic structure of the PNP and NPN junction transistor. Tarvata a common emitter lo oka pedda circuit diagram that is not so important for you. Common emitter amplifier. Circuit is not important, but I'll explain the terms. Have you copied this one? PNP lo current level emitter to bus. NPN lo bus to emitter. Clear? Now I'll try to explain what is PNP junction transistor and NPN junction transistor, and thereby we'll see what are the various terms related to that one. Okay? Common, before going to common emitter, let us see first PNP and then we'll go to that one. Okay? So, ముందు PNP అంటే చూద్దాం. PNP junction transistor. See, as I told you, in PNP or NPN, the middle portion is always, the width is very small. PNP lo ఏంటో ఎక్కువ ఉంటాయి holes. It doesn't mean that electrons ఉండవు, electrons కూడా ఉంటాయి less, because holes are majority. అలాగే here also holes majority, electrons are minor, and here electrons more, holes will be very small. And regarding doping, చూసుకోండి, doping always the left side will be heavily doped. This is lightly and this is moderately. This is moderately doped, heavily doped, and it is lightly doped. Lightly. Doping means adding impurity in P type. Okay? Heavily, moderately, and lightly. So you can see the width is very less here. So and always you can see the left side is forward bias. Left side is forward bias condition. And here the voltage also emitter, this is collector, and this is bus. So here voltage across bus emitter junction, and this right side is in reverse bias. Reverse means P type to negative terminal, N type to positive terminal. This is reverse bias. Reverse bias condition. And here voltage across bus collector junction. So this is the basic structure of PNP and if you observe carefully, it is heavily doped, moderately and lightly doped. So current, forward bias current will be in this direction, direction of current, and opposite that one direction of electron. This is the direction of current. Okay na? Alage ikkada kuda chudandi, this is the direction of current. Deeniki opposite lo electron direction. This is electron. Okay, electrons will come in this direction, electrons, and this will be direction of current. Clear? So observe carefully here. If you apply some KCL, Kirchhoff circuit, you will get IE is equal to IB plus IC. Current through the emitter, okay, is equal to current through the base plus current through the collector. You can see current is going this direction, coming here, okay, and here you can see ఇదేంటి డైరెక్షన్ ఆఫ్ ఎలక్ట్రాన్ ఇది అంటే కరెంట్ ఇటువైపు అవ్వాలి డైరెక్షన్ కరెంట్కి ఆపోజిట్ కదా ఎలక్ట్రాన్ డైరెక్షన్ ఇది ఎలక్ట్రాన్ ఇది కరెంట్ సో హియర్ ఇట్ ఈస్ కమింగ్ టు హియర్ జంక్షన్ అండ్ ఇట్ ఈస్ గోయింగ్ అవే going away. I think this will be current direction and this is electron direction. Okay, so you can apply here. This is electron direction and current will be this direction. Current direction. So here also you can see current direction coming here, going away. ఓకే ఈ రెండు చూడండి ఇక్కడ జంక్షన్ వైపు వస్తుంది ఇది వస్తుంది ఇది కూడా వస్తుంది చూడండి ఈ బోత్ కరెంట్స్ ఆర్ కమింగ్ టువర్డ్స్ జంక్షన్ హియర్ దిస్ ఇస్ జంక్షన్ హియర్ యూ కెన్ అప్లై కేసీఎల్ కిర్చాఫ్స్ ఫస్ట్ లా కరెంట్ లా సో కరెంట్స్ ఆర్ కమింగ్ హియర్ ఏంటంటే బాస్ కరెంటు అండ్ కలెక్టర్ కరెంట్ అండ్ దిస్ ఈస్ లీవింగ్ సో టోటల్ ఇన్కమింగ్ కరెంట్ ఇస్ అవుట్ గోయింగ్ కరెంట్ సో ఐఈ ఈజ్ ఈక్వల్ టు ఐబీ ప్లస్ ఐసి సో దిస్ ఈస్ హౌ ద బేసిక్ థింగ్స్ గోయింగ్ ఆన్ హియర్ అండ్ వన్ మోర్ పాయింట్ very important here ఏంటంటే అది మీకు IB in IB only 5% it was observed of total current of IE. In the base ఎంత కరెంట్ వెళ్తుంది ఓన్లీ 5% అంటే 95% ఎక్కడికి వెళ్తుంది 95% of IE is going through IC please collector. This is the basic phenomenon you have to observe in PNP or in NPN. Current through the bus is only 5% of IE, current of emitter, and 95% of current IE is through IC. This is output and this is input. This is input current, output current. Clear? So in this fashion, more majority holes kabatti ఇక్కడ కూడా మెజారిటీ హోల్స్ అండ్ మైనారిటీ ఆర్ ఎలక్ట్రాన్స్ ఇక్కడ కూడా మెజారిటీ ఏంటి మెజారిటీ ఆర్ హోల్స్ అండ్ మైనారిటీ ఆర్ ఎలక్ట్రాన్స్ క్లియర్ రైట్ నౌ లెట్ us go to the next one. I will again draw the figure for NPN second case NPN జంక్షన్ ట్రాన్సిస్టర్లో ఏమవుతుంది అక్కడ ఫంక్షన్ ఏంటో చూద్దాం ఇన్ NPN ఆల్సో ఇఫ్ యూ అబ్జర్వ్ కేర్ఫుల్లీ NPN junction transistor see in NPN also if you observe carefully in NPN see here the middle one is P small thickness N P N heavily doped, lightly doped, moderately doped. Doping means adding impurity. Again electrons, major holes తక్కువ ఉంటాయి అలాగే holes P type. Again electrons, more electrons will be there. Holes will be less అండి holes తక్కువ ఉంటాయి electrons ఎక్కువ ఉంటాయి. And again left side forward bias and reverse bias. This is voltage across emitter, this is collector, emitter, bus emitter, and this right side is reverse, P type to the negative terminal and N type to the positive terminal, voltage across bus collector or either right CB or BC, okay, plus identidi reverse bias condition. This is forward bias condition. P type positive, N type negative. P type negative, N type positive. So in this fashion also you can see here, this is the junction here. So current is flowing this direction. ఇదేంటిది ఎలక్ట్రాన్ డైరెక్షన్ ఇది ఎలక్ట్రాన్ డైరెక్షన్ దిస్ ఇస్ డైరెక్షన్ ఆఫ్ ఎలక్ట్రాన్. కరెంట్కి దీనికి ఆపోజిట్లో ఉంటుంది. ఓకే, ఇది ఎలక్ట్రాన్ డైరెక్షన్. సో కరెంట్ ఆపోజిట్ డైరెక్షన్లో. Electron is going from this side. Current will in this direction. Okay. So here also you can see this is current direction. Positive side. So electron will be in this direction. Electron direction appudu kuda current ki opposite lo untundi. Okay na? You can see coming here. And what about this one? This is coming here, this direction. ఇది ఏంటిది? ఇది ఎలక్ట్రాన్ డైరెక్షన్. కరెంట్ ఎటువైపు ఉంటుంది దీనికి. ఓకే, సో హియర్ ఆల్సో ఇఫ్ యూ అబ్జర్వ్ ద సేమ్ థింగ్, IE is equal to IB plus IC. If you apply the KCL here, Kirchhoff's current law, incoming current is equal to outgoing current. You can see here, చూడండి ఇక్కడ ఇది కరెంట్ డైరెక్షన్. ఇలా వచ్చేస్తుంది కరెంట్. కరెంట్ is coming, electrons are going. Current is coming in this direction, correct? Current. Okay, and it is going away. Here in this direction, ఏంటిది? Current direction. Electron in e direction. So in this case also, if you observe, 5% in IB of IE. Current in bus is 5%, and current in is IC is 95% of IE. It was observed. Current output in collector is 95% of IE and 5% in IB. 5% in IB of total current IE. So here you can observe there coming. Both are going away, this side and this side. It is coming here and going away. So this total sum is equal to this one. So IE is equal to IB plus IC. So here also you can observe, in this fashion the NPN junction transistor will be going on, and here the majority you can see electrons are there. So here majority are electrons and minority are holes. Holes are minority. Majority charge carriers electrons, minority are holes. You can see major electrons are there. So have you observed the things here? Current direction very clear and చూడండి. Positive side current direction, ఇది electron direction. So current will be this direction. The same here, electron current direction. ఇది current direction, electron. ఇది current direction. Coming like this current. You can see it is coming here, current. ఇది ఏంటిది? Electron current direction. So ఇది ఇలా వస్తుంది, ఇది కూడా వెళ్ళిపోతుంది ఇలాగా, ఇది ఇలా రిపీట్ అవుతుంది కరెంట్. సో కరెంట్ ఈస్ కమింగ్ లైక్ దిస్ అండ్ లైక్ దిస్. బోత్ ఆర్ కమింగ్, గోయింగ్ అవే. Both are coming, going away. Both are coming. IB plus IC coming equal to IE. Clear? So this is how NPN and PNP junction transistors, the functioning, and these are used as the amplifiers. Okay? Now we are going into the last point of this chapter, that is common emitter. Diagram is not so important for MSET. Only the formulas are important for the examination. Those I'll be giving for you. Okay? అది చాలా చాలా ఇంపార్టెంట్, అది రాసుకోండి. కామన్ ఎమిటర్ యాంప్లిఫైయర్ అండి. కామన్ ఎమిటర్ యాంప్లిఫైయర్. డయాగ్రామ్ ఈజ్ నాట్ సో ఇంపార్టెంట్ అండి. ఎన్పిఎన్ జంక్షన్ ట్రాన్సిస్టర్ యూజ్ చేస్తారు ఇక్కడ. డయాగ్రామ్ నాట్ ఇంపార్టెంట్. లెట్ us know about current gain. Current gain, these are used in the examination. They are the beta gain అంటారు కూడా, current gain or beta gain. So this beta, already I told you, IE is equal to IE, emitter current is equal to IB plus IC. Now what I will do, I will divide with IC completely. Okay, then what happens, this one I can take it as delta IE by delta IC is equal to delta IB by delta IC plus 1. This will be cancelled, 1 అవుతుంది. Now observe carefully, output and ఏం చెప్పాను? What is output? Delta IC is output. And what is input? Delta IB. Output by input. So if you write output delta IC by delta IB, this is called as beta gain. This is called as beta gain. Delta IC by IB is called as beta gain. In the same way, delta IC by delta IE, this is called as alpha gain. Current gain formula sending. Very, very important. Beta gain means output by input, and delta IC by delta IB is beta. Delta IC by delta is equal to alpha. Let us calculate alpha and beta values. ఇందాక ఏం చెప్పాను మీకు? చూడండి, బీటా వాల్యూ క్యాల్కులేట్ చేద్దాం. బీటా గెయిన్, కరెంట్ గెయిన్. డెల్టా ఐసి ఏం చెప్పాను? 95%. 95% ఆఫ్ ఐఈ బై ఐబి ఓన్లీ 5%. ఐబిలో ఓన్లీ 5%. ఐఈ క్యాన్సల్. 95% నేను ఎంత? 95/100. 5% means 5/100. So that is equal to 95/100 into 100/5. 519, sir. So the value of beta will be nearly 20 to 100. The value of current gain in beta is equal to 20 to 100 nearly. Okay? Right. Clear? Now let us come to the alpha gain. Let us come to the alpha gain. Alpha ఏం చెప్పాను? Delta IC by delta IE is equal to alpha. So delta IC ఏంటి? 95% of IE and IE. Delta IE cancel. 95%. 95% how much? 95/100. That is 0.95. That means less than 1. 0.9 kada? Less than 1. So alpha value is less than 1. 0.95 kada? And beta is between 20 to 100, please. Okay? So this is called as current gain in common emitter amplifier. Current gain or beta gain and alpha gain. Now let us give a small relation between alpha and beta. Lastly, let us give a small relation between alpha and beta. Now just now I told you what is beta and alpha. Beta and ఏం చెప్పాను మీకు? What is beta? Delta IC by delta IB. Equation 1. What is alpha? Delta IC by delta IE. Now try to apply this beta and alpha in this equation. Delta IE by delta IC. Reverse it. చూడండి. Equation 2 చూడండి ఒకసారి. Observe the equation 2. Delta IE by delta IC. So this is reverse అంటే 1 by alpha again, this one. 1 by alpha is equal to delta IB by delta IC by IB is beta. So this one I can write as beta. 1 by beta plus 1. So from this, if you take left side, 1 by alpha minus 1 is equal to 1 by beta, or 1 minus alpha by taking LCM is equal to 1 by beta, or beta gain is equal to, in terms of alpha by 1 minus alpha. So if you want alpha in terms of beta or beta in terms of alpha, you can take this value. Alpha by 1 minus alpha. And then if they ask you alpha value, చూడండి, 1 by alpha is equal to 1 by beta plus 1, or 1 by alpha is equal to 1 plus, take LCM, beta by beta, or alpha is equal to beta by 1 plus beta. Clear? So these formulas are very, very important in terms of alpha and beta. Please copy it. 1, 2, 3. Okay, right. Now let us go to the next one. Okay, clear? So these formulas are very, very, very important in the examination point of view. Alpha gain and beta gain. Now coming to the last and final one, that is voltage gain. Voltage gain. Sometimes it is written as VG or AV. Voltage gain is also written as AV. So, what is voltage actually according to Ohm's law? IR. Okay? But voltage gain in India, output by input. Output by input voltage. Voltage gain means A which is output by input. So output ఏంటి? Output IR by input IR. I output into R output by I input into R input. Output by input కదా. And what is I output? I output ఎలా వస్తుంది మనకి? డెల్టా ఐసి కదా. ఇన్పుట్ ఏంటి? డెల్టా ఐ బి. ఐ అవుట్పుట్ బై ఐ ఇన్పుట్ ఏంటి ఇక్కడ? డెల్టా ఐసి బై డెల్టా ఐబి. నా వాట్ ఈస్ డెల్టా ఐసి బై డెల్టా ఐబి? డెల్టా ఐసి బై డెల్టా ఐబి అంటే ఏంటి? బీటా. సో దిస్ వాల్యూ output by input delta current delta IC by delta I can put as beta. So beta into R output by resistance input, and this is equal to voltage gain AV. Another important formula please. Beta gain into R output by R input. Clear? Right. Please copy it. We'll go to the last one now. Power gain, power gain, power gain. Okay. So last formula and power gain ఎలా వస్తుందో చూద్దాం. Last formula, power. Generally, what is the formula of power? I square into R. So again, power gain. Power gain you can take it as AP, A suffix P. That is power gain. It is given by power output by power input, and that is what? I square output into R output by again I square input again R input. So this is power gain. So I output ఏంటి? Delta IC, okay, that is delta IC whole square by I input delta IB whole square into R output by R input, and this entire equation I can write as delta IC by delta IB whole square into R output by R input. But delta IC by delta IB అంటే ఏంటి? Beta again. So this entire thing I can write as here, see, power gain is equal to beta whole square into R output by resistance output by resistance input. So these are the formulas you have to remember so that you can do the problems very easily in the examination, please. Okay? Clear? So finally beta square delta IC by delta IB. అయితే డెల్టా ఐసీ బై డెల్టా ఐఏ అంటే ఏంటి? ఆల్ఫా. గుర్తుపెట్టుకోండి. దోస్ ఆర్ ద ఫార్ములాస్. ఒక్కోసారి ఎగ్జామినేషన్లో ఇది కూడా అడుగుతున్నానండి, అది కూడా ఇచ్చేస్తాను లాస్ట్ వన్. అదే ట్రాన్స్ కండక్టెన్స్ అంటే ట్రాన్స్ కండక్టెన్స్. సమ్ టైమ్స్ దే ఆస్కింగ్ ద ఎగ్జామినేషన్ ట్రాన్స్ కండక్టెన్స్, దట్ ఈస్ ఇన్వర్స్ ఆఫ్ రెసిస్టెన్స్. ఇన్వర్స్ ఆఫ్ రెసిస్టెన్స్. రెసిస్టెన్స్ మనం జనరల్గా జీ వాడతాం. ఇన్వర్స్ ఆఫ్ రెసిస్టెన్స్. ఓకే. సో దిస్ వన్ sometimes asking, so it is nothing but you can write output by delta IE at right. Output by delta IE. Okay na? So this is given by I input by I output by I input. I output by here I input కాదు, ఇక్కడ మనం వోల్టేజ్ తీసుకుంటామండి. ఇక్కడ వోల్టేజ్ ఐ విల్ టేకింగ్ వోల్టేజ్ డెల్టా voltage. సో సమ్ టైమ్స్ ఎప్పుడైనా ఎగ్జామినేషన్ అడగవచ్చు ట్రాన్స్ కండక్టెన్స్ అంటే ఏంటంటే డెల్టా వి అక్రాస్ బాస్ ఎమిటర్ జంక్షన్ కరెంట్ అవుట్పుట్ బై వోల్టేజ్ ఇన్పుట్. Just remember this formula. This is trans conductance, inverse of resistance, conductance. So this is given by current output delta IC by voltage input delta V BE అంటే voltage across bus emitter junction. Okay, it is given by current output by V input. Current output by V input. That's all, Andy. This is the basic things in our semiconducting devices regarding MSET and NEET. Please practice all those formulas, and regarding that you have so many numericals, and please make it. Okay? Right.